Design a laced column with two channel back to back of length 10 meter. So here this is an example for laced column. This is a beam. The beam has to transfer the load to this column. Here you are providing a lacing. You are selecting this section as channel section, that is C section. You have to design a back to back channel section for a length of 10 meter. From the bottom plate to the top will be 10 meter height to carry axial force of 1400 kilonewton. Now in this previous problem you check it, what was the load coming? 180 kilonewton. You can see that the load is very less in the previous problem. Now you have a load in 1400 kilonewton as well as the length. What was the length of previous design? 3 meter. Now this length 10 meter. If your length is increased, your column can buckle easily. Why you need lacing is load is high and your length is also high. Where you will be providing lacing is in terms of bridges. Bridges will be in much higher height. It will be not in 3 meter or 4 meter like that. Your bridges will be in a height of 10 meter, 15 meter like that. So lacings are required when load is much higher and your length of your column is also higher. Now they have given the column may be assumed as restrained in position but not in direction at both ends, that is hinged end. They have given both the end as hinged. First step is assuming the FCD. What is FCD? Design compressive stress. D is design, C is compressive, F stands for stress. Last problem 90. Since the load is much higher here, you have to assume much higher value. Assume it as 135 Newton per mm square. What is the area required? Load divided by stress will give you the area. Load is 1400, you can multiply by 1000 by 135. 10370 mm square. In problem they have given as select two back to back channel section. Now steel table ISMC 350, your value is 53.66 and your radius of variation is 13.66 and IYY is 2.38. If you multiply this area you will be getting 1073 mm square. 13.66. RZ is the strongest value, RYY is the least value. Now for design of lacing you have to take the strongest value. Since you are using a channel section you have to look into buckling class C. Your distance will be maintained so as to get that value. This back to back channel will be increased its capacity. Okay, now if you multiply divided by 136.6, 73.20. Check with the buckling class C. For 70 it is 152, for 80 it is 136. You will be getting for 73. The effective slenderness ratio of the column shall be 1.05 times the actual maximum slenderness ratio. Now what is your slenderness ratio? 23.2. Multiply into 1.05 times. The 13th point says that the effective slenderness ratio of laced column shall be taken as 1.05 times the actual slenderness ratio in order to account for shear deformation. Now the same thing you have to do here. Multiply the value into 1.05. You will be getting 76.87. Now you have to check it for 76.87. It will come under the same range only. For 70 it is 152, for 80 it is 136. Now you have to check for 76.87, 141.0. Now what is the load carrying capacity? Now you know the area and FCD. What is your area? Yeah, 10,732 into this value 141. So 1513.2, which is greater than 1400. Your load to the section is 1400. Now your section is having a capacity of 1513. Now it is safe. You have designed for strongest axis. Now you are going to strengthen that least axis by providing additional lacing. This is one channel section, this is another channel section. Now you are going to provide the lacing for this. Where is the weakest section you have to find? At the weakest section, Rx or Ry is the weakest. 2.83, which is Ry. So this x-axis is strong, y-axis is weak. So now you are going to design for the lacings. This is the top view of your lacing. You are providing two channel section. What will be the distance? If you are increasing the distance of the channel, the stability will be higher. If you decrease the distance between channels, stability will be low. You should check that what is the best distance to provide the maximum strength. Now, how to find this D? You have to match the radius of variation with Rx, Rz. Now, how will you match that? Let D be the distance. Here it is given as 220. Now, let us check how this 220 came. Let the distance be the clear distance, which is D. What is your Ixx? Ixx for this section is 10,008 and Iyy is 430.6. Cy, that is center of gravity, is 2.4. What is Cy is the distance from this extreme side to the centroid, which is known as Cx. How to find moment of inertia of combined section for a built up section? Exx is equal to area into distance square. So this is your formula. Now since you are using two Ixx, two channel section, your Ixx will be 10,008 into 2, which will be 20,016 into 10 power 4 mm power 4. This channel section is symmetrical in x-axis or y-axis. When I cut this in x-axis, I will be having two common side and the centroid will also coincide with x-axis. If I cut this in x-axis, the centroid of this channel section and this channel section will come in a single line. But if I cut this in y-axis, the centroid is for this channel section will be here. This centroid of this channel will be here. You will be cutting somewhere around here. So you have a distance. So for finding that, you have to use this formula. How to find Iyy? 2 into, why they are multiplying 2? You have two channel sections. 2 into, what is the Iyy value? They have given in steel table. Iyy is 430.6 into 10 power 4. So 430.6 into 10 power 4, this is the moment of inertia plus area, 5366. Area into distance square. Now what is your distance is? Distance from the centroid to this individual centroid of the channel. Half of that will be what? D by 2. So D by 2 plus what is the distance from this extreme side to the centroid, or Cy, center of gravity of Y. What is Cy is? Distance from the centroid to this extreme fiber distance, that is Cyy, 24.4. Now you will be adding this D by 2 plus 24.4 into square. This Iyy is for a built up section. How will you find I plus area into distance square? You can check the moment of inertia concept. Why they are multiplying by 2? Because you are using two channel section. Ixx just they have multiplied by 2. Why? Because their center of gravity lies in the same plane. Equating Iyy to Ixx, we get this answer should be equal to your Ixx. Now your Ixx is 2016 into 10 power 4. Only one known is D. Now how will you do this? Take down this 2016 divided by 2. If you simplify, you will be getting D, 218.4. If you round off, the distance D will be 220 mm. What are the things you have done? You have tried a channel section. It is safe. If you provide 220 mm distance, the moment of inertia is same in y-axis as well as x-axis. You are having both the moment of inertia equal. So this section is a symmetrical section. Now you have strengthened your section. Your design is over. Now you are providing this lattice, that is lacing system. Lacing shall be provided with an inclination of, what is the angle which is given? 40 to 75. Here they have tried 45-degree angle. So this angle of lacing from the horizontal is 45 degree. What is your load coming? 1400 kilonewton. Horizontal spacing is 220. How much should be extended? If you are using one bolt, what should be the width of the lacing? Minimum width of lacing? 3 times the diameter of bolt. Now you assume that 20 mm dia bolt. Let us use 20 mm dia bolt. if you multiply 20 mm into 3 times 60, so you have to extend your lacing up to this point and 60 here and 60 here. So totally what is the length of the lacing? 220, which is this distance, plus you additionally need 60 plus 60. So totally what is the horizontal spacing? 340 mm. Now what is the vertical distance? This is horizontal distance. How to find from this point to this point? Your angle is 45 degree. Do you know adjacent side? This is the opposite side. Find this vertical spacing. You can use tan theta. Tan theta is what? Opposite side by adjacent. Now adjacent 340. Opposite has to be found. So now you apply tan 45 equals x divided by 340. Now what is this 2? From a single point to the next point, you are having 2 half, isn't it? So this is a single triangle and you have to multiply by 2. So your vertical spacing is into 2. So you will be getting 680 mm. Least radius of one channel, which is 28.3. 28.3, which is your least radius. You have to strengthen this. Strength of your lacing. You have to find the slenderness ratio. Vertical spacing is 680 divided by least radius of variation is 28.3, which is 24.03, which is lesser than 50. Your lacing slenderness ratio should not be greater than 50 mm. Now what you have provided is lesser than 50 mm, which is 24.03. Now that point is okay. Since you are only having the axial force, the design criteria 2.5 percentage of load acting. Since it is in percentage, you can divide it by 100. 35,000 Newton. Single lacing you can keep 35,000. If you are using double lacing, you can divide it by 2. The shear force coming to lacing is 17,500. Let us check either this force can be resisted. We can find the length of this lacing. You know the horizontal distance and vertical distance. Cos 45, adjacent is 340 and hypotenuse is x. You can cross multiply and you will be getting hypotenuse as 480 mm. Now you have the length of your member is 480. What is the force coming here? 17,500. Take the design capacity of your lacing. Thickness of lacing is, you have a class that 1/40th of the length, 480. 480 by 40 is 12 mm. The thickness of the plate required is 12.02 mm. Now you can try with 14 mm flat. The minimum width of the lacing what we have provided is 60 mm, which is 3 times the bolt. Now assuming the dia of bolt 20 mm, 3 times the bolt is 60 mm. R radius of variation equal to root of I by A. Flat is a rectangle section. What is the width of the flat? 60 mm. What is the thickness of the flat? 14 mm. And the rectangle has a width of 60 mm and 14 mm. What is the cross sectional area? 60 into 14. How to find moment of inertia for rectangle? BdQ by 12. Your breadth is 60, width is 14 divided by 12. Now you know I and A. If you root that, you will be getting R. 4.04 mm is your R. Slenderness ratio of lacing, KL by R. What is K? Since this is bolted connection, you are using one bolt, both the ends are pinned. Length of your lacing is 480, which is the length, and your radius is 4. 118.97, which is lesser than 145. In the design points which I have given, they have mentioned that slenderness ratio of the lacing should be less than 145 mm. Now your lacing is less than 145 mm. What are the things you have done in this design? Selected the section, the length of your lacing 480. Now what is the distance from this point to, from here to half is 340, totally 680. Now what is the distance between this two lacing? Horizontal distance is 340. Now what is the thickness of the lacing? 14 mm. What is left? See, you have designed a section, lacing is good. How many bolts is required to connect that? How to design the connection? First one is check for shear. For a single shear, 0.785 d square divided by 4 into 400 divided by root 3, 1.25, which is factor of safety. Assuming 4.6 grade bolt 45,272, which is 45 kilonewton. In the previous problem I said that if you are using 20 mm dia bolt, what will be the load carrying capacity? 45. First one is shear strength is over. What is KB, which is the least of the three parameter? 30 divided by 3 into 22. E is edge distance. 30 divided by 3 into 22 is 0.45. Strength in bearing. Strength in bearing is 2.5 times KB is 0.45. D is diameter. T, which is the thickness. Now you will be getting these values. This is 45 and this is 12150. 5 is least. How many bolt is required? How you can find this? Your force coming here is 17,500 divided by 45,000. If you divide this 0.387, at least you need one bolt. So if you round off, this will become one bolt. So now here you are providing one number of 20 mm dia bolt. Now this is the last step. Check for strength of lacing. So you have provided everything. Now you are checking for the strength. That is KL by R. You have already found out. This plate is 118.97. Since this is a solid section, you are having the class of C. See, for a solid section, the buckling class is C. What is your value? 118. For 110, you have 94.6. For 120, you have 83.7. Now, you can find for 118. Your answer will be 84.2. Now, you can multiply this FCD into area. What is area of this section? 60 into 14. 71,251. The force coming in this lacing is 24,749, which is very less when comparing to the strength of lacing. Hence it is safe. Providing 60 ISF 14 at an angle of 45 degree, you will be providing one bolt and 20 mm diameter. This is your lacing design.